Hi there, we're going to solve a fun little geometry puzzle from Catriona Ag, who regularly shares these sorts of puzzles over on Twitter, so you can check her out if you're interested in seeing more of these. A lot of the comments on this particular problem were providing some good solutions and wondering if you could do it without trig, so I figured it'd be fun to show you a solution today that does not use trig. And here is the problem. We're given a square, and the square has an area of 36. Now we've got this right-angled triangle. You can see the right angle is right there. And this triangle is such that this vertex bisects, or is the midpoint of this side of the square. So this segment here is congruent to this segment here. Using that information, we want to find the area of this green right-angled triangle. Give it a shot yourself before watching the rest of the lesson. For my solution, we're going to use analytic geometry. So we'll place this diagram in a coordinate system and then find the vertices of our right-angled triangle. And then we'll use this formula, which I've been covering in my Algebra 2 class, which is why it was at the front of my mind. This formula for calculating the area of a triangle with its three vertices using a determinant. If a triangle has these vertices, we can put them in a 3 by 3 determinant like this. Calculate that, multiply it by plus or minus a half to make it positive, and that is the area of the triangle. So to get started, let's place this diagram in a coordinate system. And what tickles my fancy would be to make this point the origin, where the triangle hits that midpoint of a side of the square. We'll call that 0, 0. Of course, we can place this diagram in a coordinate system however we please. Let's place it in the coordinate system so that point is the origin. Now, what are the coordinates of the other important vertices in our diagram? Let's start with the vertices of the square. We know the side length of the square because we're told that it has an area of 36. So let me go ahead and use a dotted line here. If the area of the square is 36, then its side lengths, of course, are square root of 36, or just 6. If the side length of the square is 6, we can figure out these vertices. Let's start with this one here. Since this is half of this whole side of the square, its length is 3, because the square has sides of length 6. So the coordinates of this vertex right there are going to have to be 3, 0. It's still got a y-coordinate of 0. This is just a straight line on the x-axis. And then what about this point up here? Well, it's this point just moved up 6, a whole side length of the square. So the coordinates of that point are 3, 6. This point over here is pretty similar. It's going to have coordinates of -3, 0. And then this one up here is -3, positive 6. Those are the coordinates of the vertices of our square, which also includes this vertex of the right triangle. To use our determinant formula for the area of a triangle, we need to know the coordinates of the three vertices of the triangle. Right now, we are just missing the coordinates of this vertex. So the game plan to find it will be to find the equation of the line containing this side of our triangle, and then to find the equation of the line containing this side of the triangle. Find where they intersect, that's the point we're looking for, and then we can use our formula. So let's start off with finding the equation of the line that contains this side of the triangle. In order to find the equation of a line, we just need 2 points, and we have 2 points, 0, 0, and -3, 6. We'll use those 2 points to find the slope of the line, and then write the equation in point-slope form. So let's write out the work for what we'll call line L1. To find its slope, we'll use slope formula, and I'll just call that m. If we take these 2 points, the slope is the change in y divided by the change in x. So that's 0 minus 6, the change in y, divided by 0 minus negative 3, the change in x between those 2 points. And that's equal to negative 6 divided by positive 3. That is a slope of negative 2. So for our line L1, what is its equation? Let's use point-slope form. We've got our slope. For our point, let's pick the origin, because that's a very nice and easy point. So putting this in point-slope form, y minus 0 equals the slope, negative 2, times x minus 0. And that, of course, means that y equals negative 2x. Very nice and easy equation for the line containing this side of the triangle. Now we just need the equation for this other line, and we'll go ahead and call that line, let's say, L2. I'm going to go ahead and shrink this box with the little bit of work that we did for line L1. How are we going to find the equation of line L2? To find the equation of a line, we need a point and a slope. We have a point on L2, but what is its slope? Since we don't have another point on L2, that makes it a little bit difficult, but it's not too difficult because remember, this is a right triangle and this is our right angle. So in fact, all we have to do is find the slope of this line, and since that's perpendicular to line L2, we'll have our slope for L2 using a quick negative reciprocal, if you remember anything about perpendicular slopes. So let's just figure out what is the slope between 0, 0 and 3, 6. I'll start writing in purple here for line L2. The slope between 0, 0 and 3, 6 is the change in y, 6 minus 0, divided by the change in x, 3 minus 0. This is 6 over 3, which is 2. That's not the slope of line L2, that's the slope of this line that's perpendicular to L2. So the slope of L2, we'll write it here, m, is the negative reciprocal of 2. That is negative 1/2. So now we've got the slope of L2, we've got a point on L2, we can write its equation using point-slope form. That's going to be y minus the y-coordinate, 6, equals the slope, negative 1/2, times x minus the x-coordinate of 3. And we can go ahead and simplify this a little bit. Negative 1/2 times x is just negative 1/2x, and negative 1/2 times negative 3 is positive 3/2. We'll also add 6 to both sides. So we're going to have y equals negative 1/2x plus 3/2 plus 6. How many halves are in 6? That would be 12 halves. So 3/2 plus 6 is 15 halves. So this is y equals negative 1/2x plus 15 halves. That's the equation of L2. All right, so line L1, if you remember, had an equation of y equals negative 2x. And we just figured out that line L2 has an equation of y equals negative 1/2x plus 15 halves. Now remember, these are these two lines, this one and this one. So now we're just solving a system of linear equations to figure out where they intersect, which is this point right here. And once we find that point, we can calculate the area of the triangle because we'll know the coordinates of all of its vertices. So let's just go ahead and solve this system of linear equations. Since they're both solved for y, let's just use substitution. Y is negative 2x. So we can write that negative 2x, putting this in there, negative 2x is equal to negative 1/2x plus 15 halves. Then I'll go ahead and add 1/2x to both sides. So negative 1.5x equals 15 halves. And then we just have to divide both sides of this equation by negative 1.5. Dividing both sides by negative 1.5 gives us that x equals negative 5. If x equals negative 5, and y equals negative 2x, then y has to be negative 2 times negative 5, and so y is equal to 10. And that's where our lines intersect. Those are the coordinates of this last vertex of our right triangle. The coordinates are negative 5, 10. Let me just bring that point a little bit closer to that vertex, something like that. Negative 5, 10. Now we know the coordinates of all three vertices, and we can go ahead and use this formula for the area of our triangle. And here's how the formula works. The area will be plus or minus a half times the determinant of. In the first column, we put the x-coordinates of our vertices. The order here doesn't really matter. We just need to make sure that the y's match up with the proper x's. So for the x's, let's say our first x-coordinate is 0 at the origin. Our second x-coordinate will be 3 at that point, 3, 6. And our third x-coordinate will be the one we just found, negative 5. And then in the next column, we have to put the corresponding y-coordinates. 0, 0, so we've got 0 corresponds to the x-coordinate of 0. And then the x-coordinate of 3, that had a y-coordinate of 6, so that goes there. And then our x-coordinate of negative 5 had a y-coordinate of 10. And in the last column, you just put a few 1s. And now we just have to calculate the determinant of this 3 by 3 matrix. If you don't remember how to calculate determinants of 3 by 3 matrices, let me remind you of a quick way to do it. Here is the determinant that we've written. Just take the first two columns and rewrite them next to the determinant. So I'll just do a quick copy and paste here. And just to make it clear that these numbers don't really have to be there, we're just doing this to help our calculation, I'll make them green. And then all we have to do is take the top to bottom diagonals. Those look like this: 0, 6, 1, 0, 1, negative 5, 1, 3, 10. Take those diagonals, multiply, and add them together. So let's do that part first. So we'll take 0 times 6 times 1, which is 0. Again, we're multiplying those individual diagonals. So we're going to add to this 0 times 1 times negative 5, that's 0. And then add the next diagonal, 1 times 3 times 10. That's going to be positive 30. So plus 30. So we just multiplied those individual diagonals and then added them together. And then you're going to do the same thing for the bottom to top diagonals and then subtract that from this first part. So let's do that now in red. You want to look at these bottom to top diagonals. Negative 5, 6, 1, 10, 1, 0, and 1, 3, 0. We're doing the same thing. We're adding them up. Those will go here, and then we'll do the blue minus the red. All right, so we've got negative 5 times 6 times 1, that is negative 30, plus 10 times 1 times 0, plus 1 times 3 times 0, so that's just plus 0 plus 0. And that's how you calculate the determinant of a 3 by 3 matrix. This turns out to equal 30 minus negative 30, so 30 plus 30, so 60. That's the determinant. And so our area, remember the plus or minus is just here to make sure our final answer is positive. We'll just use positive half then. Our area is going to be 1/2 times the determinant we just calculated, which was 60. And so the area of our right triangle is 30, or if you want to say it, 30 units squared. So that's a fun way that we can calculate the area of this right triangle that's partially in this square using algebra and determinants and no trigonometry. Let me know in the comments if you have any fun solutions that you came up with.